This is video 3 for the magnetism unit. So in this one, let's talk about your home. The electricity that comes to your home is kept right around 110 volts. So if you have no lights turned on, no refrigerator, no heaters, nothing turned on, the voltage would still be 110. However, the current would be 0. You see, things that use electricity draw current from the wall. So if you have like an electric motor, it's going to draw current. Um, if you start turning on more and more lights in your house, you start drawing more and more current, more and more amps. The power company works very hard to keep the voltage at 110, even when you start using more appliances. So since power is like a voltage times a current, or a current times a voltage, the way we can calculate how many watts is to take 110 and multiply that by amps, because the 110 will be constant. Now, the appliances are usually marked with their power requirements. A hairdryer requires so many watts to operate. So if you want to calculate how many amps it takes, just take the power and divide it by 10. You have P is voltage times current, then current would equal power divided by voltage. So with that power rating divided by 110 volts would tell you how much current it would use. A bright light bulb that uses 110 watts then would take right around 1 amp. A heater that uses 550 watts then would take 5 amps. Now, the amperage add. So if you have the light bulb and a heater running at the same time, you would need 6 amps. 1 plus 5 is 6. If you exceed 15 amps, generally you would blow a fuse. Now, this can be kind of a pain in the neck. So that's why we have multiple fuses. Power coming into your house then gets sent along different fuses or different lines. So you may have a series of outlets that are connected to just one fuse. That way you can have a second series, or maybe an oven connected to a different fuse. So if you, that way you don't blow a fuse every time you try to bake a tasty lasagna and turn on a light at the same time. So we can put these, each of these things that use electricity on their own fuse so we don't exceed that 15 amp max. Now, to get to your house, the electricity travels along high tension power lines. These travel at very, very high voltages, around 500,000 volts. So the reason for this is that the power, since it equals voltage multiplied by current, if the power needs to remain constant, a high voltage means that you can have a low current. And the lower the current, it reduces the, there's going to be less heating in the wire. Because since the current becomes less, you don't need to worry about the resistance in the material in the copper wires as much. But remember that your house runs on 110 volts. So we have to have this device that converts the low current, high voltage, high 500,000 volts, down to a high current, low voltage for your home to use. And that device is called a transformer. What a transformer does is it steps the voltage either up or down. And that's actually going to be something we're going to discuss in our next unit when we talk about induction. So we'll get into the science behind transformers. But what a transformer does is it would convert this super high voltage, 500,000 volts, going down these high tension power lines, and it steps it down to 110 volts. That's a little safer for your home to use. So down here, just a couple examples of maybe like the different types of power lines you might see and their usual distances. All right, changing gears. Now we can start talking about magnets. I'm sure you're very familiar with magnets. We use them on refrigerators. We use them to close refrigerator doors. We use them everywhere. So basically, what exactly is a magnet? Well, um, magnets create these magnetic fields around them. And here's a quick little example of a magnetic field. We see that's a magnetic field between a north and south pole. Here's another magnetic field between two south poles. And what happens is we got three classifications of materials. We've got ferromagnetic, paramagnetic, and diamagnetic material. So ferromagnetic, there are only three ferromagnetic materials: iron, cobalt, and nickel. These three materials are strongly attracted to a magnetic field. So if something's made of iron, cobalt, or nickel, steel is basically iron with carbon in it, those materials would be attracted to a magnetic field. Paramagnetic materials are materials that are weakly attracted to a magnetic field. Diamagnetic materials are materials that are weakly repelled by a magnetic field. So that's basically what the magnetic, how magnets affect materials. Now, once we get a magnet, if we have like a bar magnet, we notice that opposites attract and likes repel. And we differentiate these magnets with the north and south pole. And the reason why we call like the North Pole is because if we suspend it from a string, it will align itself and point towards the geographical North Pole of the Earth. And the other side would then be called the South Pole. So, getting a little deeper into this, we have three types of magnets that we can create: permanent, temporary, and electromagnetic. And a permanent magnet is going to be materials that keep their magnetism. So, like bar magnets, those would be an example of a permanent magnet. Temporary magnets are ones that you can create one by taking a permanent magnet and dragging it across some ferromagnetic material like iron, and eventually that material will become magnetic just for a quick time. Or if you were to touch a ferromagnetic material with a permanent magnet, that magnetism would be transferred through it for a short while. Eventually, this material will lose its magnetism, though. The third type is called an electromagnet, and it's created by electric currents. What's interesting about these is that these can be turned on and off. So you see these in scrap yards picking up heavy pieces of metal. Now, the way these originally came to be, the first known magnets were natural rocks, and early people didn't know this, but it was containing iron ore, and it was known in English as lodestones. So a feature of these stones was that if you suspend them, they tend to rotate until one end is pointing north. And as you might imagine, this completely revolutionized travel. If you're in the sea at night, you use the stars to, guide your ship. But if it's cloudy, you can't see the stars. There's no way of knowing how to orient yourself. So we can use magnets to orient it. And this was a very, this was so important. This was a very, very technological advantage for countries that had this, technology, this magnet technology. For hundreds of years, nobody understood why one end of the lodestone points north. And it turned out that the Earth itself is a gigantic magnet, and the lodestone was simply being manipulated by Earth's magnetic field. We call these lodestones now compasses. So something that might be interesting, the Earth's geographic North Pole is actually the South Pole of a very large magnet. And the geological South Pole is actually a magnetic North Pole. Here's a picture of one of these lodestones. They cut them and shaped them into like a spoon shape so it would float in some water. And then they'd have one end that points, and then it always point towards geographic North Pole. So another major discovery was that you could make brand new magnets from iron. So if you take a needle and rub it with a magnet in one direction, you can make a new magnet. It'll be temporary, so you'd have to redo this every now and then, but it's a useful way to make magnets instead of trying to mine for magnets. And then, another feature of these lodestones is that there's a force of attraction that draws them to each other. It's almost mystical how that can work. Magnetism also comes from moving charges. So we know that there's a force on magnets that pull them together. And really, we've learned that it's just another aspect of electricity. So there's a force between electric charges that occurs only if the electric charges are moving. So for that reason, you can think of magnetism as a force that occurs between electric currents rather than between stationary charges. So if I take two wires and have currents moving in the same direction, there will be a force that will draw those two wires together. And here's just some math here. You don't need to know it, but here's just some math that helps to illustrate how much force is pulling these in. One other feature, we tend to use the capital letter B for magnetic fields. Again, I'm not entirely sure why, but we do use the letter B for magnetic fields. So modern permanent magnets, such as those that are used for refrigerator magnets, compasses, door latches, they don't seem to have any electric current. But we now know that permanent magnets do get their magnetism from electric currents. The electric current for the permanent magnet is inside the electrons. Electrons spin, so they are moving charges, and they make tiny little currents. So due to the electron spin, these atoms have magnetism. It's very hard to detect this magnetism, and if there are many electrons and they're all spinning in random directions, the magnetism tends to cancel. So in this case, most materials are diamagnetic or paramagnetic because a lot of their electron spins cancel out. However, in ferromagnetic materials, the electrons from the different atoms tend to line up and have the same spin direction. So those little those little magnetic fields, which we call a moment, they all add together to make a large magnetic field, and then those materials can become a permanent magnet. And the reason why they're permanent is because they retain their magnetism without any need for additional power. So it was once thought that one electric charge can put a force directly on another electric charge. We now think that there's something intermediate that might be happening. The electric charge creates something that we call an electric field that fills up the space. Since all charges create their own fields, this interaction of the electric fields tend to result in electric forces. So this field theory helps us explain why like charges attract each other and opposite charges repel. gravity is going to work in the same way. Things with mass create a gravitational field, and then these gravitational fields interact, creating gravitational forces. Magnetic fields work in the same way, where we have this region around a magnet, which we call this magnetic field. And you might notice that the magnetic field looks very similar to the electric field. There's a lot of similarities between electricity magnetism. So we can use these field theories to help us explain common interactions like electric forces, gravitational forces, and now magnetic forces. Now, if you put a wire into the right geometry, you can arrange it to exert a very strong electric force on other currents, or a permanent magnet. So a common geometry is called a solenoid. This is basically just taking a coil of wire and wrapping it up so that it forms a cylinder. It's just once we do this, if you turn the electricity on, you will have a strong magnet. Turn the electricity off and it stops being a magnet. Reverse the flow of the current and you reverse the polarity. By reversing the polarity, you switch the north and south poles. So these electromagnets are very helpful in industry for, we use them in scrap yards, obviously, to pick up metal, but we also use them in your cars to lift and lower the locks on your doors if you have electric locks. So in this picture up here, we got a simple electromagnet. It's just a coil of wire and a cylinder, which we call a solenoid. And when we turn on the electricity, depending upon which way the current comes in, so if the current's going this way, so it's going in the bottom, out the top, we have north and south. If we switch this so that it's going in the top and out the bottom, the poles will switch. If we insert a ferromagnetic material like an iron nail, it will increase the strength of the magnetic field, because the atoms, which we call domains inside the magnet or inside the iron, will align itself to create an even larger magnetic field. We call that induced magnetism. The thing though is, once you turn off the current, that nail will still be a magnet for a little while. We also use magnets in recording. So using this induced magnetism, we can create things like videotape, computer hard drives, MP3 players. So in these devices, a very small electromagnet induces magnetism in a very small region of a magnetic material. So those tiny little regions are given polarities of north, south, 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 whatever. And then it can be read as binary, 1, 1, 0, 1, 1. So in this way, we can store information. So what we do is in a like a hard drive on a computer, we get the spinning disk, and we use a little tiny magnet that records little norths and souths, and that makes binary. So there's a very good reason why you should keep your computer away from strong magnetic fields. It could destroy that. Now, heat also destroys magnetism. If you heat up a material, its atoms vibrate, and for a magnet, that means the electron spins, which were originally all pointing in the same direction, can come out of alignment. Marie Curie discovered that at a certain temperature, all permanent magnetism disappears. So every material has its own Curie temperature at which this happens. And then finally, we can use magnets to make electric motors and generators, and that's actually going to be something we're going to talk about in our next unit. So a little longer video, but this will conclude our unit on electricity and magnetism.